All right. So today we're talking about circles and specifically tangent lines and how they relate with circles. So first off, let's define a couple line segments. In general, the new one to most people would be the chord. So a chord is any line segment that starts and stops on a circle, or specifically on the same circle. So we define it as a line segment who has both endpoints on the same circle. So one endpoint here, the other endpoint here, both on the same circle, okay? A radius you guys have dealt with a lot in the past. That's any line segment starting from the center and going to any point on the circle. And the very definition of a circle is the collection of points that are equal distant from the radius, equal distant from the center. So you can swing that same radius in any direction, and that same line segment all the way around is always congruent to that original. Okay, so I wrote all radiuses, or radii, depending on how you want to say it, are congruent. Now think about a chord. Now a chord, I could draw any 2 points, right, connected, and I could do it this way. And chords, if the points get closer and closer, the chord gets shorter and shorter until the points come essentially together and you get something incredibly short that, you know, approaches zero, but you can't actually get to zero because then that'd be a single point and not a line segment anymore. But if you think about getting longer and longer until they're antipodal, they're on opposite sides of this circle, the furthest they can be is across from the center, and that right there creates the diameter. So down here, the diameter, one way to define is just the longest possible chord of a circle. Another way is it is a chord that passes through the center of a circle. So as long as it passes through the center, that goes from one side all the way to the other, or from the top straight down, through the center to the other side, or in any direction. Take any point, connect it to the center, and then keep going through, and you hit the circle a second time, and that gives us a diameter. And again, all the diameters are the same, because it's just twice the length of that single radius, because you have one radius here, plus another on this side, totaling up to twice the radius. Okay, so now looking at, those were all line segments, now let's look at lines. So a line really has three possibilities. The line could lie totally outside the circle, in that case we just called it a line, or it could pass through the circle in 2 points. We call that a secant. So it's any line that passes through a circle in 2 distinct locations, okay? 2 distinct separate points. Now, if we were to move that secant closer and closer to the edge of the circle, those 2 points at which it hits the circle get closer to closer. And for just a split second in time before we totally separate the line outside, there is an instant when it is touching just one single point. And that single point we call the point of tangency, and this line segment, this line that passes through that one point we call a tangent. So a tangent is any line that, so a line is infinite in both directions, passes through a circle in exactly 1 point, just skims off it and touches just for a moment and keeps going, right? This wouldn't be the case if we drew some line segment or ray that hit and stopped and then went out. That doesn't count. This has to be a full line, so infinite in both directions, that just touches for a sliver of an instant there, okay? And that's all the vocab we're going to introduce here. So logically, that one point where a tangent line hits, we call the point of tangency. But really, we've got a tangent line, a secant line, or a chord. Those are really our 3 new words. Okay, so I'm going to add one more thing too. Since the beginning of the year, we've really only assumed one thing. And that assumption is if you look at a picture and a line appears to be straight, you can assume it's a straight line. That way, you know, if you get 2 lines that look like this, you go, well, those are both straight lines, so these are vertical angles. You can make that assumption. We're not going to say, oh, it was actually 179.5 degrees. So if a straight line, then it is a straight line, okay? Now we're going to add 2. If something appears to be a tangent line, then it is a tangent line. So for example, if I draw a circle and I draw something like this and put a dot there, that looks like it's a tangent. I don't need to explicitly say that. You can assume that's a tangent line. Okay. Secondly, points. if a point looks to be near the center of a circle, you can assume that's the center of a circle. And if a point looks to be the point of tangency, you can assume that that's the point of tangency. Okay? And that's just going to save a few sentences at the beginning of every problem we assign with circles. So you can assume that point is the center, and you can assume that line is a tangent. Okay? All right, so let's get started. So how many tangents can we draw when two circles either do not intersect, or what I'm gradually doing here is I'm sliding these two circles together, right? And then they could touch right here for a single point, and then down here they'd now pass into one another, and then here one is totally inside of the other, and then the next logical step would be something that looks like this, okay? So how many lines could we draw here that are tangent to both of these? Well, on the first one, we could definitely draw a line that's tangent to both of these like this. Okay, I did a poor job, but that's okay. It's just a sketch. We could also draw one on the other side like this. Okay, but where else could we draw tangent lines? Well, there is the other option of putting one that passes through the interior of the two, like this, and then mirror image, you could do one that passes through like this. So that was not a good estimation. Let's make a really big point. Okay? So there's 4 lines tangent to both of these circles at the same time. Now, totally separately over here on the right, we could start off with those same 2 tangent lines that we had in the last one, and we get something like this. Okay? But are there any more? And in fact, if these 2 circles are tangent to each other at a single point, there's exactly one more, right? Right through here, okay? If they're overlapping now, we can see again, we can start off with those 2 tangent lines on the outside, but now there's no way to pass through this middle region without hitting a circle, because there is no gap. They're overlapping. It's not like the last one where you could squeeze through by a hair on our chinny chin chin. Now there's nothing. If we try and pass through this region, for sure we're going to hit something here, and for sure we're going to hit something here. So there's no other internal line there. And then finally the last one, now the circles are tangent to each other, but one's inside of the other. So in this case, we only get one tangent line that's tangent to both, and it would look like this. So that's a nice type of problem you might come across, right? Now, really, tangent lines only have 2 properties. So the first one is that a tangent line is perpendicular to the radius at the point of tangency. Now, I like to think about this rather than as a written out proof. I like to think about this just as symmetry. So if I have a circle with a dot in the middle, obviously I could cut this and I could say, okay, well, obviously a circle is symmetrical from left to right, right? Each side has half a circle. They're identical in every way. So I think about if I have a tangent line that intersects the circle only at point, I could just rotate this picture, right? Let's see if I could just rotate this picture until that point is directly on top, right? It doesn't matter where I put that point. It's just rotating my circle. So I'm going to rotate till my point's on top. So that point is right on my line at the top. So here's my line passing through. Well, if there's only one point where it touches, and on the right side, if I were to just let me just take some white here. If I were to just cover up one side of this image, there's nothing special. Whoa, that's too much. There's nothing special about the right side that would, by any logical sense, be any different than the left side, right? They both have half of that line intersecting at a point and half of a circle. So by all logical sense, they should be symmetrical. And so I like to think of this as, well, then that would mean, not rigorously proven, but that would mean that this angle right here would be the same as this angle right here. And if 2 angles are the same and they add up to a 180-degree straight line, that means they must both be right angles. So that's my logical way to look at it, but that's not a written out proof. Those sort of assumptions can sometimes get you into trouble, but that helps me remember what's going on. Now, really what this means, though, is if we come across a right angle, this means now we can use Pythagorean Theorem. So we've got a squared plus b squared equals c squared sometimes. And again, this would be if we have a triangle. And we could also use some trig, right? Some SOHCAHTOA, sine, cosine, tangent. So whenever I have that right angle coming up, I'm thinking I could always draw a triangle and figure out a missing side length, a missing angle, using either Pythagorean theorem or trig. So it's just a little mental trigger to come up when you have a right angle. So let's look at the types of problems we'd come across here. So find the value of the variable. And sure enough, they connected the center to some point on the tangent line. So you've got a right angle and a triangle. So now you can use both the Pythagorean theorem and trig. Now in this case, we can't use trig because we don't have two sides, right? We don't have this side. There's a variable in the hypotenuse. So trig wouldn't be the most enticing option here. However, we could definitely use the Pythagorean theorem here to find the value of the variable. So we're looking for r. So we could say, okay, well, a squared plus b squared equals, and the length c of our hypotenuse is r plus 16 squared. Okay, so if we write that out, we've got r squared plus, this is 576 equals, and now on the right, you know what people want to do is they want to say, oh, well, that's r squared plus 16 squared, of course, but we know that's not true, you know, from our area models and past discussions. So to actually figure that out, we go r plus 16 times r plus 16, and we multiply out these binomials. So we get r squared plus 16r, and then plus 16r plus 16 times 16, which is 256. So over here, we get that that's r squared plus 32r, just combining our like terms, plus 256. So to solve a quadratic, our first step is get rid of all the parentheses, combine like terms, and then move it all to one side. Okay, so now that we've gotten rid of all of our parentheses, we've combined our like terms, let's move everything to one side. So let's just get all this stuff from the left and move it over to the right. Okay. So now what we've got is 0 equals, and oh look, there's no more r squared. So we've got 32r equals, or sorry, minus 320. And so now it's just a linear equation. So we can go back to our old strategy, just let's move all the numbers to one side, variables to the other. So we get 32r equals 320. So dividing both sides by 32, we just get that r is 10. Now there's two things to double check. One is that what the question was asking for? Find the value of the variable. It was. Second, plugging it back in, do we get a real side length? Like is there a side length of 0 or negative? But no, a radius of 10, that would mean the hypotenuse was 26. Yeah, that seems totally workable. All right, let's go down here. This one says, now for this problem it says determine whether AB is tangent. So it's saying specifically don't assume that it's tangent in this picture and try and prove, is this tangent? Well, we know if this is tangent, this should be a right angle, right? So if it's not a right angle, then we know for sure it cannot be, right? That would be the contrapositive, right? So if tangent, then right angle. So if we could find not right angle, the contrapositive we know to be true, then that would mean it is not a tangent. So let's check this really quick. And so we get, we could use Pythagorean theorem. A squared plus b squared equals c squared, which whether it's equal or an inequality would tell us whether it's an acute right or obtuse triangle. So I could just plug in 9 squared plus 15 squared and see if it's equal to 18 squared. But you know what? I'm doing this in my head. So instead, I want to reduce this. I'm going to divide each side by 3. And I get a similar triangle that is 3, 5, and 6. And I want to see if this is a right angle. Okay, so I'm going to instead deal with the easier numbers. So is this equal to 6 squared? Well, we get 9 plus 25. That's 34. Is that equal to 36? No, it is not. And so we know that not a right angle then means not a tangent line. So no, it is not a tangent line. All right, so our second property coming up here is if we have any point outside of a circle, okay, there are two tangent lines we could draw. We could draw one either if you were looking straight at the circle from that point, you could go to the left or you could go to the right, right? Any other point, sorry for the bell here, any other point would just take you out into empty space if it was outside of those two, and if it's inside of those two, it would pass through the circle in two different points and be a secant, not a tangent. Okay, so there's two tangents from any point outside a circle, and our property says, well, the two segments created from that point to the circle, from the point to the circle on the other side, are congruent, right? And again, this all just, to me, it just comes straight from symmetry, right? I could absolutely just cut this picture down the center, and you know, on one side you have, and again, I'm just going to do my fat white here to erase, on one side you have half a circle, and you're connecting a point to the circle, so of course, okay, that's you know, makes sense. We did it. We drew from the point to tangent to the circle. But if you have the same point, the same distance away from the same half a circle, why would it matter if the circle's upside down? It's still the same point and the same half a circle. So you'd get the same exact distance. So that symmetry, again, helps me just see why they work, and logically it helps me remember things kind of at a deeper level with those connections. So that symmetry says those are connected. Now, interesting little side note, and this will come up kind of often throughout this chapter, is if we have a circle and we connect a point outside to two tangents and then connect into the radius, what shape do we get? So I'm just going to use pink here. Well, we know these are right angles. We know these two line segments are congruent, and the other two line segments are radiuses. So we at least get a kite. Now, would it be possible to get something else? If we slide this point in enough, what we could actually get is, that was not a good drawing, but we could actually get a square if all the sides were equal, because they would all be 90 degrees. But at least the fact that this is a kite will come up off and on, and we will use what we know about kites from the last unit on some of these problems. So just something to think about. But at least we know that those two line segments are congruent. All right, so how you would use that is pretty straightforward. You would see a problem like this, and you'd say, oh my gosh, look at that symmetry, top and bottom. Those two are congruent. So we just say 3x plus 10 equals 7x minus 6, and use some algebra. So taking 3x from both sides, adding 6 to both sides, 4x is 16. So we've got x equals 4, and again, just to double check, one thing is find the value of the variable. Okay, so we did find the variable. Just plugging this in really quick, we get a positive side length, and we get a positive side length. If we did everything right, should be congruent, so it all checked out. So I'm going to do a couple practice problems on IXL. If you feel solid enough already, you can go ahead and try some problems on your own, or stick with me. Okay, so starting out, it says WX is tangent to circle V. So that gives us a lot of information here. That tells us that this is the center. That tells us that since this is tangent, we can assume, it doesn't say clearly, but this is assumed to be the point of tangency. And so we have a right angle. So now we've got a Pythagorean theorem here. Again, you could reduce this triangle by 2 and deal with a triangle that's 3, 4. Oh, and we know our Pythagorean triple, that's a 3, 4, 5 times 2. So it's a 6, 8, 10 triangle. So that missing side is 10. Or you could have just used the Pythagorean theorem and you'd get the same thing. All right. So let's get out of here. We got, again, tangent. So here's the center. Here's a right angle. And this time it wants us to find the measure of angle n. So if we want to find this angle right here, we would say, okay, well, 41 plus 90 plus, let's call it x, equals 180. So subtracting 90, we get 41 plus x is 90. And really, in a right triangle, we always know those other two angles are complementary. So we take away that 41 minus 41, and we get x equals 49. Okay, so this one, what is xz? So this is similar to the first one we did. So we've got no common factors, so we got to figure out 8 squared plus 15 squared equals c squared. So that's 64 plus 225. That's 289. We take the square root of that, and we get square root of 289, which is 17. You could notice this was actually a Pythagorean triple, if you're comfortable with that. Okay, another one asking for the angle here. So we've got, what is angle H in our picture? Now again, we know that since this is tangent, we've got a right angle. So these two must add up to 90. So we get 90 minus 48 would give us 42 degrees. Okay, another problem of the same. So we've got a right angle, and then 47, so 90 minus 47, we get 43. Okay, so now this kind of almost looks like two tangent lines, so you might want to jump to the assumption that, oh look, like this and this are congruent, but that's not the case because actually this is a secant down here. So let's look at what we've got. So ST is tangent to Q. So we know that this is a right angle because that one's tangent. What is the measure of angle U? Oh, so this is just the same type of question, just looks a little different. We still know it's a right triangle. So these two add up to 90. So 90 minus 26 would be 64. Okay. Another one of the same, so we've got its tangent here. We're looking for n, so 90 minus 30, that's 60. Okay, what's MP? So again, this is Pythagorean Theorem, so I'm going to simplify this by 4, and we get that this is 3, 4, and so we know this is a 5. If we multiply it back by a factor of 4, we get 16, 12, and the last one would be 20, just recognizing a Pythagorean triple. Okay, looks like all these are the same. I believed there was going to be another level of difficulty. It might not come on until we get to level 80. So I'll just stop this after another, let's say, 2 problems here. Oh, so here we go. So here's the other type of problem I was looking for. It took to 64. So this one, it's saying both are tangent. And if they're both tangent to the circle and they both go through this point, what we know is that these two must be congruent. So we know x minus 1 must be equal to 7. It's asking what is the value of x. So we're going to add, 1, add 1, and we get x equals 8. So what is the measure of h? Well, if these are both tangent, then we know that this is a right angle and is a right angle. And we know every four-sided quadrilateral totals 360 degrees if you add up all the interior angles. So let's call this x. And we know that x plus 90 plus 47 plus 90 equals 360. And then I'm going to take away these two 90s, and what I get is x plus 47 must be equal to 180. Subtracting the 47, we get that x equals 133. And again, that came from the fact that tangents are perpendicular, and on top of that, the total of any four-sided figure is 360 degrees when you add up the interior angles. So that's 133. And we'll end up stopping there. The rest of the problems will be some permutation of this. They're just mixing in more variables. So we know here, again, this is a right angle. So we know that these two add to 90. So you set up your equation is equal 90, and they just become a little more algebra heavy. but the same idea. It's just practicing more and more. So I hope you enjoyed this video. Now go ahead and try it on your own.